Good afternoon or morning, everyone. My name is Kumudini Redicharla, and today we are going to dive into the fascinating and mysterious world of dark matter. Although it makes up a significant portion of the universe's mass, we can't see it directly, making it one of the most puzzling phenomena in modern physics. In this presentation, we will explore the discovery of dark matter, the evidence supporting its existence, the leading theories behind its composition, and the current and future efforts in its detection. So, in today's presentation, we are going to cover the major four aspects of dark matter, which involves the historical perspective, the leading theories behind this dark matter, the detection efforts our scientists have put into and are still in the process of detecting it, and the experimental landscape. So let's get started. The story of dark matter begins in the 1930s with Fritz Zwicky's observations of the Coma cluster. He noticed that galaxies within the cluster were moving much faster than expected, indicating the presence of some unseen mass. Then, in the 1970s, Vera Rubin's groundbreaking work on the galactic rotation curves revealed something even stranger. She found that galaxies rotate at a constant speed at their outer edges, which defies our understanding of Newtonian physics. These discoveries laid the foundation for the research for dark matter. Now let's dive a little deeper into these early observations. Zwicky's measurements of the velocity dispersions in the Coma cluster showed that galaxies were moving much faster than they should based on the visible matter alone. This pointed to the existence of dark matter. Similarly, Rubin's work on spiral galaxies revealed that stars at the outer edges of galaxies were moving at a constant speed, suggesting the presence of unseen mass providing additional gravitational pull. Now, let's talk about some of the strongest evidence we have for dark matter. First, galaxy rotation curves. As I just mentioned, the stars on the outer edges of galaxies are moving much faster than expected, implying there is more mass than we can see. Another piece of evidence comes from gravitational lensing, which occurs when light from distant objects is bent around massive objects. This distortion of light shows the presence of unseen mass. Finally, the cosmic microwave background, or CMB, contains fluctuations that support the existence of dark matter, further solidifying its presence. Since now that we know dark matter exists, the next big question is, what is the composition of this dark matter? Scientists have proposed several candidates for the composition of dark matter. So, what is dark matter made of? Scientists have proposed several theories. One of the leading candidates is weakly interactive massive particles, or WIMPs. These are heavy particles that interact weakly with ordinary matter. Other possibilities include axions, which are extremely light particles, sterile neutrinos, heavier versions of the neutrinos we're familiar with, and primordial black holes, which could have formed in the early universe. Each theory has its strengths and weaknesses, and the experiments are currently underway to test their validity. Now let's talk about the third most important aspect of our presentation regarding the dark matter, which is the detection efforts, which involves the direct and indirect methods that scientists have used to detect what dark matter is. Detecting dark matter is incredibly challenging because it does not interact with light in a way that we can observe. However, scientists have developed both direct and indirect methods for detection. Direct detection involves experiments where we try to observe dark matter particles interacting with ordinary matter in underground laboratories. Indirect detection looks for the products of the dark matter, annihilation, or decay, like gamma rays or cosmic rays. Additionally, high energy particle collisions in accelerators like the LHC could potentially produce dark matter particles. Let's now take a look at some of the major experiments dedicated to finding dark matter. Projects like Xenon, Lux Zeppelin, and Super CDMS focus on direct detection using liquid xenon or cryogenic methods. For indirect detection, we have Fermi-LAT, a gamma ray space telescope, and HESS. These experiments are already pushing the boundaries of our understanding, and the future looks promising with increasing sensitivity and new technologies set to provide better data and new approaches to dark matter detection. While dark matter is the leading explanation, there are alternative theories. One such theory is modified Newtonian dynamics or MOND. MOND suggests that gravity behaves differently at very low accelerations. This could explain galaxy rotation curves without the need for dark matter. However, Mond struggles to explain other large scale cosmological observations, and it has not gained widespread acceptance within the scientific community. So, to conclude, dark matter is still one of the biggest unsolved mysteries in science. While we have compelling evidence for existence, we still don't know exactly what it's made of. However, the future looks bright as ongoing and upcoming experiments promise to shed light on this dark and mysterious substance. The search for dark matter is not only about understanding the unseen forces of the universe, but also about revolutionizing our knowledge of physics and cosmology. Thank you for your time, and I look forward to any questions you may have.